Welcome to qnawire.
In this problem, we're going to analyze a combination gas-steam cycle. So here's our the gas cycle up here from 5 to 7 to 8 to back to 5. And then at 9 is where we have a heat exchanger. So we're extracting the heat from the hot exhaust gases. And essentially, well, I mean, basically, we're actually, in this cycle, we're just kind of pulling in new air all the time. So there's really not this is not really a process from here to here. So basically, we're just extracting the heat as it comes out from here. And then it's not a closed loop for a gas turbine because we're just using air as the working fluid. So we don't basically have a closed loop where in the steam cycle we almost always have a closed loop here, although we wouldn't necessarily have to. Then let's see here. So if we look at the gas side, we can use ideal gas laws. So from 6 to 7, we can figure out the temperature using ideal gas relationship. And so we have because we know the pressures at 6 and at 7, which I didn't write down. So let me see what the gas side. Let's see here. Well, we know the pressure ratio is 16, so we know that's what we know. P6 over P5 is 16. So that's the pressure ratio. So we can figure out the temperature here by knowing the pressure difference between from here to here. I'm looking at the wrong thing. From here to here is the pressure difference of 16. And it's isentropic, so we can just use the isentropic with ideal gas formulation and using these heat capacity ratio. So in the end, we get a temperature up here right here of 662.5 Kelvin, up from 300 Kelvin here. This is Kelvin. This is also in Kelvin. So these temperatures here are in Kelvin. Let's see here. So we can figure out the heat transfer into the air because it's just the mass flow rate of the air, which we know, 14 kilograms per second, times the difference in enthalpy from here to here. And the difference in enthalpy, we'll just use the constant heat capacity, which may not be such a great idea because we got a pretty big swing in temperature here, but we'll use maybe an average. What did I use here actually for the heat capacity? I didn't write the value down. Let me find the problem in my notes. Let's see here. 77. Okay, I used a heat capacity of 1.005. So use CP equals 1.005 kilojoules per kilogram Kelvin. So that I think is pretty much just room temperature air, if I remember right. So that's probably not a great estimate for, I mean it's all right for, it's 300 Kelvin, but up here at 600, up here to 1500, maybe not so good. But it's an estimate. We could do better by using tables or using reduced, adjusting it using reduced pressures and temperatures and stuff. Now in the compressor, from 5 to 6, so here's our compressor. So basically instead of a pump, we have a compressor. And again, we can figure out the change in enthalpy by using, a constant heat capacity. And we get I guess I never said the heat in is about 11.78 megawatts of heat coming in here. And then the work into the compressor is about 5.1 megawatts. So we can see that actually, in this cycle, in the gas cycle, the compression work is considerable. Where in the steam cycle, the pump work is very insignificant. Again, we have an isentropic process here, so we can figure out the temperature at 8, and knowing the pressure ratio from 7 to 8, which is also well, it's 16 from here to here again. So again, the pressure ratio between 7 and 8 is 16. So here we use 1 over 16, and then the heat, the exponent here, and we get a temperature at 8 of 679.3 Kelvin. So it's just slightly above what it was at 6. So we can figure out the work out of the gas turbine, mass of the air times the change in enthalpy, again using a constant heat capacity. And so we get a work out of the gas turbine of 11.55 megawatts. So that's pretty good. So let's see here. Then we have what else do we have here? Now we're going to move on. Oh, so then we can get the net work out of the gas cycle. So that's this minus this. So basically running the compressor from the turbine. So we're siphoning off this amount. So we wind up about 6.45 megawatts. So now from here on down, we're looking at the steam cycle. So again, it's basically the same thing we've been doing in the last 20, 30 problems or something. So enthalpy at 1, we can figure out saturated liquid at 15 kilopascals. So we can figure out the specific volume. That allows us this times the change in pressure gives us the specific work into the pump. Conservation of energy on the pump says that this plus this gives us the enthalpy out of the pump, so that's H2. We know the pressure and temperature at 3, where we're given, so we can get the enthalpy and entropy there. We know the pressure at 4, and the entropy at 4 is the same as that is at 3. So we have 2 thermodynamic properties, so we can find the quality factor. We're in the 2-phase region here. And we can find the enthalpy at 4. And now we can look at the heat exchanger. So the heat exchanger is essentially, basically right here. It's not here, but it's, this hot exhaust gas is the heat exchanger process coming in here. This is like the condenser, kind of the condenser for the cycle, if you think about it that way. So we get a temperature down here at 9 of 400, and that was given to us as 420 Kelvin. So in the heat conservation of energy on the heat exchanger says that, well, this is essentially I've split up the energy in and the energy out. So the energy in is the steam from, this is the energy out. Yeah, the energy out, and then the energy out of from the energy out from the steam and the energy out from the air, the energy in from the steam and the energy in from the air. So I just separated them out. But anyway, so it's basically just energy in equals energy out, but rearranged a little bit. So then we know everything in here except for m dot s, and so we can figure out that the mass flow rate of the steam is 1.275 kilograms per second. So quite a bit lower than the mass flow of the air. All right, so then we can figure out the work done by the steam turbine. It's mass flow rate of the steam times the change in enthalpy over the turbine. And so we get about 1,384 kilowatts. The work from the pump, so we know now the specific work into the pump. Now we know the mass flow rate through the pump, so we can get the power into the pump is about 13 kilowatts. So that gives us the net work out of the steam cycle, and that's 1,371 kilojoules or kilowatts. And so the net work out of everything is then this plus, where is it? This guy here. And that winds up being about 7.8 megawatts. And so if we can look at the total net work out from both turbines, subtract the pump work and subtract the compressor work. So the total net work out from both cycles is this value, and the total heat that we put in from the combustion process was this value here. So we can take this and divide it by this, and we get 66.4%. So we can see, obviously, we have a much higher thermal efficiency than we were typically getting in just the pure steam cycle, even when we had all kinds of regeneration and all kinds of other modifications to try to improve the efficiency. So we're really high here. But again, gas turbines are not, you're dealing with really hot and combustion. This is not an easy thing to do because a gas turbine basically is an expensive piece of equipment, obviously. So, it's not as simple as just, oh yeah, we'll just throw a gas turbine cycle, a gas cycle on top of this old power plant that we had that used the Rankine cycle. So, but again, if you're building something new, you can definitely think about that. This would be possibly a good option to see if it makes sense. I mean, obviously, it's all going to come down to economics, but it's worth checking out.